Okay, next talk is by Yuri Makarychev, and he's going to tell us about approximation algorithms for satisfiable and nearly satisfiable Fourier CSPs. Please.
Thank you. So thank you for coming to my talk. I will talk about algorithms for satisfiable and nearly satisfiable ordering CSPs. And before I define before I define ordering CSPs, let me give an example of a specific ordering CSP called betweenness. In this problem, we are given n variables, x1, etc., xn, and m constraints, and all constraints are of the following form. xa lies between xb and xc. Now, the goal is to arrange the variables on a line like this so as to maximize the number of satisfied constraints. And formally, let's say that the solution to this problem is a permutation pi of length n, and it defines an ordering of x's as follows. So x1 is at position pi of 1, x2 is at position pi of 2, and so on. And for example, for this specific ordering, the permutation pi is 4, 3, 1, 5, 2, and here x1 is at position 4, x2 is at position 3, and so on. And here's an instance of betweenness. We have 5 variables and 6 constraints. At the bottom of the screen, you can see a possible feasible solution. And it's not hard to see that in this specific example, 4 out of 6 constraints are satisfied. And here you can see that all of the constraints of this form, xa lies between xb and xc for some indices a, b, and c. Because in this example, 4 out of 6 constraints are satisfied, we will say that the value of this solution is equal to 4 over 6, or in other words, 2/3. Now let's define a general ordering CSP. And to this end, we need to fix an ordering predicate phi of some arity k. So in other words, it depends on k variables, x1, etc., xk. And it is defined by a Boolean formula with atoms of the form xi less than xj. And here you can see some examples of ordering predicates. The first one is the one that we have already seen, the betweenness. The second one is perhaps the simplest one, the simple precedence predicate, which just says that x1 is less than x2. And here you can see some, just kind of an arbitrary ordering predicate of arity 4. And we will actually talk about this specific ordering predicate a little bit later today. Now, the main question that we are interested in this work is the following. Let's fix a predicate phi, or more generally, a constraint language. And now, given an instance of ordering CSP with predicates with predicate phi, what fraction alpha of the constraints can be satisfied as a function of the optimal value for this instance in polynomial type. And it will be convenient for us also to talk about the set of satisfying ordering of a given predicate phi. So what is it? That's simply the set of relative orderings of variables x1, etc., xk, on which the predicate depends. So that's a subset of permutations of length k. And for example, for the simple precedence predicate, this set consists of a single permutation 1, 2. And for the betweenness predicate, the set of satisfying ordering consists of 2 permutations, 2, 1, 3, and 2, 3, 1. So you can see that for any satisfying solution, x1 is at the second position. Therefore, kind of here, pi of 1 in this set is always 2 for both permutations. Now, there is a very simple, kind of trivial approximation algorithm for any ordering CSP. The algorithm ignores basically the input and returns a random permutation from the set of all permutations of length and uniformly at random. In other words, it randomly permutes x1, etc., xn. And it's kind of standard and straightforward that each constraint is satisfied with probability equal to the number of satisfying orderings over k factorial, and that's also the expected number of satisfied constraints. And we will use this quantity as the baseline for our algorithms. Of course, it doesn't make any sense to design an algorithm whose approximation ratio is worse than that or even equal to that. You want to get something better than this trivial approximation. And sometimes it's possible, sometimes it's not. Now, let me mention what is known about this problem. And let's start with kind of bad news. Guruswamy, Hosted, Manakaran, Raghavendra, and Charikar showed, loosely speaking, that for every predicate phi, there is no non-trivial approximation algorithm if opt is less than 1 minus epsilon, where epsilon greater than 0 is a fixed constant. So if you have an instance which is 0.75 satisfiable, we basically cannot do anything better than just output a random solution. And because of this result, which is based on the Nigham's conjecture, we need to focus on either completely satisfiable instances or 1 minus epsilon satisfiable instances where epsilon is like little o1, very small. Another important result is due to Badirsky and Kara. So let's ask the following question. Suppose that our CSP is completely satisfiable. Let's assume that our instance is completely satisfiable, and then the question is, can we actually find a solution that satisfies all the constraints in polynomial time? So we are not interested in an approximation, we want to get an exact algorithm. And Badirsky and Kara provided a complete classification of such CSPs based on phi, and in some cases it's polynomially tractable, in some cases it's NP-hard. And actually the criterion is pretty simple, so given a specific predicate phi or even a constraint language, we can easily say whether it's polynomially tractable or NP-hard. Now in this work, we are interested in two problems. So for the first problem, let's assume that CSP phi is not polynomially tractable, so we can't solve such instances exactly in polynomial time. And then the question is, what fraction alpha of the constraints can we satisfy in polynomial time, and particularly whether alpha is better than the trivial bound. And there was only one previous result addressing this problem due to Shor and Sudan, who showed that for betweeners we can get alpha equal to 1/2, and the trivial guarantee for betweeners is 1/3. And the second question is about the nearly satisfiable regime. So now let's assume that our instance is 1 minus epsilon satisfiable, and epsilon is little o1. And our question is, can we satisfy some sign beta minus big O of log n, log n epsilon fraction of the constraints? So if epsilon is sufficiently small, then it's very close to beta. And the only result previously known for this regime was by Evan, Naor, Shiber, and Sudan. And they designed an algorithm for the minimum feedback arc set problem, which in this context gives an algorithm with beta equal to 1. So in this work, we provide a general framework for solving these problems for any predicates phi or even constraint languages. And in particular, we show that there are infinitely many ordering CSPs that have non-trivial approximation in the satisfiable regime and in the nearly satisfiable regime. And specifically using the procedures that we derive, we show that there are at least 15,051 ordering CSPs of verity 4 that admit a non-trivial approximation in the satisfiable regime, and at least 843 ordering CSPs of verity 4 that admit a non-trivial approximation in the nearly satisfiable regime. Now let me show how our algorithms work. So that's kind of a high-level view. And to simplify things, let's just focus on the completely satisfiable case. So given a predicate phi, let's say that phi prime is a polytractable relaxation of phi. If, first of all, it's a relaxation, meaning that the set of satisfying ordering of phi prime contains that of phi, or in other words, if every solution that satisfies phi also satisfies phi prime. And second of all, CSP phi prime is polynomially tractable. And at the first step of our algorithm, we replace every constraint of the form phi of xi1, etc., xik, with the corresponding constraint phi prime of xi1, etc., xik. Now, since it's a relaxation, the obtained instance is completely satisfiable if the original one was completely satisfiable. And because CSP phi prime is polytractable, we can actually solve it in polynomial time and actually even in linear time. So we solve it and we get some permutation pi. Now, the bad news is that pi as is doesn't have to satisfy any original constraints. So it satisfies all the constraints in the relaxed instance, but not necessarily in the original one. And now we choose an appropriate sequence of random permutations sigma t. So for every size t, we have this family of random permutations sigma t, not non-uniform permutations. And we apply permutation sigma n to the obtained solution pi. So pi prime is equal to sigma n pi, and that's our solution. Or in other words, we permute the obtained ordering using our permutations. To be more specific, let's consider an example. So this is an ordering CSP of arity 4, which we discussed, which we saw before. And it's not hard to see that if phi is satisfied, then x2 is less than x4. So phi prime, this phi prime is a valid relaxation. And moreover, it's polynomially tractable, and we can actually solve it using topological sort. So we get this solution. Let's say we get this solution, right? Now we do the following. We take two copies of the solution and put one of them to the left and another one to the right. And we have an ordering of variables x1, etc., xn, in which every variable appears twice. So that's kind of not a valid ordering. Now, to get a true ordering, we do the following. We take every variable xi and keep only one of its copies. Each copy with probability 1/2, and do that independently. So we get a solution, and it turns out we can show that using our framework that in expectation we satisfy 1/4 of all constraints, but the random algorithm satisfies a 1/6 fraction. So that's significantly better. Now, the main challenge with this approach is how do we choose this infinite family of permutations, of random permutations. There is no succinct representation for that, or even finite representation for that, and our goal is to optimize over them. And we do that as follows. First, we identify a class of regular random permutations, very regular structure, and we show that these permutations are as good as arbitrary permutations. So we can focus on those, and then we provide the complete classification of permutations of sequences of permutations from this family, and it turns out that the combinations in a certain sense of the identity decreasing and uniformly random permutations with appropriate weights, and the problem reduces to optimizing these weights. So basically, we reduce the problem of finding the optimal rounding scheme to a continuous optimization problem, and we can find, the best rounding scheme from this family with any desired precision delta. And the algorithm is very practical, so we actually implemented it, and found 15,051 ordinary CSPs of Verity 4. To summarize, we designed a general framework for solving satisfiable and nearly satisfiable instances of ordinary CSPs, and using this framework, we show that many ordinary CSPs of Verity 4 admit non-trivial approximation in the satisfiable or nearly satisfiable regime. And also, I haven't had a chance to talk about the techniques, but the framework actually connects various fields of mathematics, including permutation densities, permutons, the theory of permutation descents, the Ramsey theory, exchangeable and contractible arrays, and Rozborov's theory of flag algebras. The main open problem is this framework optimal in the sense that is it true that for every ordinary CSP, this framework provides the best possible algorithm, rounding scheme, or maybe there are better rounding schemes outside of this framework.
Thank you so much. So we have time for questions.
Can you briefly explain how this framework connects to Ramsey theory?
So the step where we go from an arbitrary sequence of random permutations to a very regular one, we multiple times, like infinitely many times, apply the Ramsey hypergraph theorem.
That was another hand.
Yes, so related to your open problem, is it true or the weaker version would be like, does this framework always improve upon the naive random sampling thing? Or
No, for some ordinary CSPs, it doesn't provide any improvement. But kind of my conjecture is that the fact of life. So for these CSPs are not these CSPs are approximation resistant. Yeah.
What are the standard complexity assumptions, UGC?
Whatever you want. I mean UGC or whatever.
Let's thank the speaker again.